Hello friends. Welcome back to this series on Docker. We are going to see how to install and set up Docker on our Windows operating system. So without any further ado, let's get start the session. So first let's see, what are the system requirements for installing the Docker desktop application on our Windows operating system? So for installing Docker on your Windows operating system, you need to have at least Windows 10, 64-bit, with Pro, Enterprise, or Education version. Then, Hyper-V and container Windows features must be enabled. And some other requirements. 64-bit processor, with second-level address translation. 4 GB system RAM. And BIOS-level hardware virtualization support must be enabled in the BIOS setting. I know, some of you are confused with second requirement, which is Hyper-V and container Windows feature must be enabled. So let's verify that. So for verify that, here, you can simply search for Task Manager. Open it. Click on Performance. And here in the CPU, you can see that virtualization is enabled. So this virtualization needs to be enabled. By default it is enabled in our Windows operating system. So you don't need to any extra thing unless you manually disable this feature. So to install Docker, simply search, Install Docker on Windows. Here simply click on the first link which says, Install Docker Desktop on Windows. Here you can see, Download Docker Desktop for Windows. So let's just click on this button which is going to start download this executable file. Now as you can see, it is successfully downloaded. So to start the installation, I am going to click on it, so it will start the installation. So as you can see the installation is started. The first window here is configuration. Here I am going to leave everything as default, and click OK, which is going to unpack all the files. The installation process is pretty easy I guess. We just need to click some buttons and Docker will be installed. So now you can see, this Docker desktop is successfully installed. So I am going to click Close. Now here, I will click on this Docker desktop icon, which is going to start the Docker desktop application. Here we need to accept the term and conditions. So I am going to click on Accept, and click on Next. So here as you can see, my Docker desktop homepage. Now one thing I will recommend here, is to sign in with your Docker credential. Here I have already logged in, you can create your account and then you can log in to this. And after log in, you will able to see your Docker if here. So now let's get started with the Docker. So here I am going to open my command prompt. Here you can just type, docker, -version or v and here you can see the version which we have installed. Now let's check if Docker is working with Docker Hub perfectly fine or not. So to check this, you can run, docker, run, hello-world. So run this command. So here you can see the output. We can see on the first line it says unable to find image hello world latest locally. Then it has pulled this image from the Docker Hub repository. And once the pull is complete, here you can see the status, downloaded newer image for hello world. Then it says hello from Docker. So that means, everything is working fine with your Docker, and it's able to run your Docker images and this is the first image we have run. So guys, this is how we can download and install Docker on our Windows operating system. So guys, we will see some basic and frequently used commands in Docker. This is going to be a very easy and interesting session on learning the Docker basic commands. We will see all the very basic commands and frequently used Docker commands. So without any further ado, let's get start the session. So here, I am using the Windows command line. If you are on Mac you can use your terminal. And if you are on Linux, then you can use the Linux command line. Now here, the only prerequisite is must be installed on your system. And this we have already learned in the earlier session how to install Docker. Now here, the very first command is, docker, version. As you can see this command gives us the information about the Docker client, and the Docker server, which is the Docker engine. Here we get the information about the version of the Docker client, then API version, the Go programming language version, and similarly for server, we get all this details. So this is going to be a very handy command if you want to look at your client and server version. Now the next command is docker -v. So this command only gives us the version of Docker. So as of now, I am on Docker version 20.10.16. Here also you can use docker -version, which will be the same command, and it will give the same output. Now let's see our next command, which is docker info. So this command gives you a little detailed information about the Docker that is installed in your system. So here you can see, the very first section gives us the number of container, running, paused, stopped, and number of images. As of now, we do not have any images or container, so we are getting 0 for all these fields. Then the server version, the driver details, plugin information, and all other information. So if you want to have some quick look information on the Docker that is running in your system, you can run docker info command. Now let us come to Docker images. So the first command is docker images. This gives us the list of all the images we have. And of course here we do not have anything. So we use the other command to pull the image. Here I can say docker pull. And here I can give the name of any image. So if you are on Docker Hub, you can get any images. Here I will go to explore repositories. Here you can get any repositories. For example, let me say I want to get an Ubuntu image. So I will search for Ubuntu and press enter. And here you can see the Ubuntu image. If you click on it, it will show you the details. And here you can see the docker pull command, docker pull Ubuntu. So here I will say docker pull and then Ubuntu. You can see, it will use the latest tag by default if we do not provide it. And it is now pulling it from the library. And yes, it is done now. And now, if I say docker image, you can see, now it is showing us Ubuntu. And this image was created or updated 13 days ago, and this is the latest tag. Now our next command is docker rmi. Using this command we can remove the one or more images. So here we need image_id to remove image. So I will copy this image_id and paste it here. And now here you can see, this is now deleted. And now if I say docker images, now I don't have any image. Now let us come to container. So for container, the very first command is docker, then ps. So this command is used to list the containers. So here, as of now I don't have any containers. So what I can do is, I can use the other command, which is docker run. This command is used to run a container. Now for example, I am using docker run, and I will say Ubuntu. Now we have already deleted our Ubuntu image. So the Ubuntu image is no longer available on our system. So if I say docker run Ubuntu, you can see it says, unable to find image locally. So now it will start pulling it from library, which is Docker Hub. And then it will start the container. So you can see, it has downloaded the image. And now if I say, docker ps, you can see, still we do not have the container running. However we have the image, but we do not have the container running. So in case of Ubuntu, what we can do is, we can say, docker run, and we can use the -it flag. So if I go to docker run --help. So here you can see, the flag I is for interactive. And flag T is for allocate as sudo tty. So in the simple language, here we want to start the Ubuntu system, Ubuntu container, and log into it, or start the command prompt of Ubuntu. So here I will say, docker run -it for interactive, then I can say Ubuntu. Now we can see, we are inside Ubuntu container, and we are on the Ubuntu system. So if I say, ls, you can see, we are now actually inside Ubuntu. So now, if I run the command, docker ps, I should get the container running. However I cannot run it here, because we are inside the Ubuntu, so I am going to open a new command prompt. Now here if I say, docker ps, now you can see, the container running, and this is the container ID. So now we can run the commands, like docker start and stop. So let's say, docker start, and this container ID. So it will start the container. And docker stop, and the container ID will stop the container. So now we have stopped. And if we go back, here you can see, it has automatically come out of that container. and it is now on our local system. Now let us see some system command. So here the first command is docker stats. This command gives us the details on the running containers, memory usage, the input-output, and so on. So let us try to again run our container. So I will say docker run it and Ubuntu. Again we are inside Ubuntu. Now here, you can see it is already showing us memory usage and all. Then we have another command, which is docker system df. So this command is used to check the disk usage of Docker. You can run this command, and it will give images, container, local volume, build, and the size which is being taken by all these Docker elements, and all the information about disk usage. Now let's see the next and last command, which is docker system prune. So this command is used to remove all the unused data. Here you can see, it is giving me a warning. This will remove all the stopped container, all network not used by at least one container, all dangling images, and all build cache. So here let me first say, and let me show you all the image and container which are there as of now. So I will say, docker images. You can see we have just an Ubuntu image. And if we say, docker ps, here we have one container running from the Ubuntu image. So now if I run the command, docker system prune, and I say why, here you can see the total reclaimed space. And again if I say docker images, here you can see my Ubuntu image is still there. And if I run the command docker ps, here you can see my container is still running, because this container was running and the image was being used, so it didn't delete them. So now here if I say docker stop and pass the container ID, so it will stop the container. So now if I say docker system prune and -a, you can see it is giving me a warning. This will remove all stopped container, all network, and all images without at least one container. If I say yes, it will remove all the unused data. So now if I say docker images, you can see the image is deleted. So be very careful while using this command, which is docker system prune. So guys, these are the top basic commands in Docker. In this video, we will talk about Docker container and Docker engine. So without any further ado, let's get start the session. First of all, let us talk about what is a Docker container. So, a Docker container is a loosely isolated environment, running within a host machine's kernel, that allows us to run application-specific code, along with all of its dependencies. Alright, now that we have our definition of a Docker container, now let's dive into some of the concepts that the definition brings up. So, let's discuss how Docker relates to a kernel. By answering first, what is a kernel? So in operating systems, like Mac OS, Windows or Linux, the kernel is a software at the core of the machine, with complete control over the entire system. It handles reading input and output from various software applications, and also turning that data into instructions for the CPU to execute. This core software also handles things like memory, and devices like keyboards, monitors and speakers for the entire operating system. So how do Docker and the kernel relate? Docker must run on top of a machine kernel, in order to provide its features. This original kernel is what we call the host machine, and you'll often hear or see the concept of the host machine appear related to Docker. So know that this refers to the original computer, and its kernel where Docker is running. Alright, to further understand how containers work, we need to see, or rather understand the Docker engine. We just brought up the idea, the Docker can be running on top of a machine's kernel. So let's go through this more thoroughly. What exactly is running? The system in place, that handles Docker services is called the Docker engine. The engine consists of a server process to run Docker features, then an API that we can use to launch those features. And finally, a command line interface client, that allows us to interact with that API as users. The server is also called the Docker daemon. A daemon in operating systems is a term to refer to processes running in the background. So the Docker daemon is running in the background, without you having to directly interact with it. It runs within the kernel of the host machine. It then listens for requests from the user. We users send those requests through a command line interface that the Docker engine exposes. And then once the daemon receives those requests, it does a heavy lifting of actually creating containers. The Docker daemon is like a construction team that operates within the host machine's kernel. It has a book of blueprints per se that defines how it should create various Docker-related objects like containers. And this book of blueprints is the API. Then US clients, the users of Docker, can tell that team to use a specific blueprint through the command line. With that blueprint, the Docker daemon knows how to construct containers on top of host machine's kernel foundation. Now, with this diagram, let's illustrate how the Docker engine works and its relationship to containers. So here we have the elements that construct the engine and how it relates to Docker containers. Again, the engine is made mainly of that Docker daemon, managing Docker objects, the Docker command line interface, and the Docker REST API that acts as a layer between the command line and the daemon itself, to provide blueprints on how to work with Docker and create Docker objects like containers. So this diagram illustrates an operating system that is running Docker. The running Docker daemon sits and operates right on top of the host's operating system's kernel. It acts as a layer between the command line that interacts with it, as well as the containers that it creates. The command line application, which is provided by the operating system, such as a shell, like a terminal, or PowerShell in Windows, interacts with an interface provided by Docker to work with the Docker daemon. As users, again we send requests to the daemon to create containers. And as daemon receives those requests, it creates those containers within the host machine. So the main point of this diagram is to illustrate the Docker command line interface, working with the Docker daemon on top of the host machine's kernel. Let's move on and continue exploring containers. Now that we have a grasp of the Docker engine, the kernel, and the host machine, let's think about how Docker container environments actually work. The Docker engine creates these environments called Docker containers on top of the kernel where you can run application-specific code. Now, what does this environment provide? The environment allows for a certain degree of loose isolation. For example, the processes or running instances of a program within one container should not be able to affect the processes of another one. Also, a container environment allows for resource limitation. We can specify how much of the CPU each container is allowed to consume. Likewise, we can say that each container only has access to a maximum amount of kernel memory. This allows us to make sure certain apps don't hug too much of the host machine's kernel resources, allowing all the containers to run fairly. This loosely isolated environment then allows us to run application-specific code, meaning we can run an application within one container, and then bundle all that application's dependencies within that container, without having to install those dependencies on the host machine. So one of the big things about containers is that it gets its whole own file system. So all the application-specific code will exist within that container file system, including all of its libraries and dependencies. For example, if we have a Node.js server running in the container, all of those Node module libraries can be installed just within the container itself, without those having to be downloaded or created on the host file system. This becomes especially useful when you had multiple container environments and applications running on your system, but you won't necessarily need to support the entire environment or directories in libraries of all those applications, all within your host machine. You can just support them within their own containers. Now I hope you all guys understand the work of Docker container and Docker engine. Now, in this session, we will discuss Docker image. So without any further ado, let's get start the session. So in the previous session, we show what is Docker container and how it works. But we have an important question that remains. How is the Docker containers create? Docker containers are created by objects in Docker, called images. An image as defined by Docker is a read-only template with instructions for creating a Docker container. These instructions define everything that the container needs. What the container will need to run, its specific software, including any dependency code, libraries, environment variables, or configuration files for research, limitation, networking, etc. These instructions are collected within an executable package, which is the image itself. So when you run that executable package, you create the Docker container. Therefore, the container is the instance, or the result of executing those instructions outlined in the image. For example, these images can tell Docker to create a container that runs Ubuntu, one of the most popular Linux operating system distributions. Or we can have an image that tells Docker to run Nginx, a notable web server. Later on, we'll learn how to create images in this customized way with a special kind of file called the Dockerfile. In the Dockerfile, we outlined the instructions for how the image will create the container. In the meantime, let's go over that image to container relationship once again, because it's an important concept to grasp within the Docker. The Docker image is the assembled set of instructions, which outline how the container should be created. It's assembled into one overall image, which is why we can create an entire Ubuntu container by using its assembled image. Now, the container is a result of running that image. Docker looks at the assembled image and executes those instructions one by one to create a container. So now the container is created by using all of those completed instructions and executing them all. In an analogy often used to illustrate this image to container relationship, is a class-object relationship of object-oriented programming. The Docker image is what the class that defines how to create the objects of the container. From the class, you can create many instances of the object. Likewise, from the image, you can create many instances of the container. Now let's learn where to find the already most widely used images created by Docker users around the world. In order to find these images, we look to Docker Hub. Docker Hub collects images from Docker users, from independent developers to entire engineering organizations, like MySQL and Ubuntu, which allow for anyone who knows how to use Docker to use them within their containers. Hosted as repositories, these images on Docker Hub allow you to look at different versions of an image that have been published over time. Alright, so let's check out an example of an image on Docker Hub. So here we have a Ubuntu repository on Docker Hub. Here we are, as you can see, this is hub.docker.com. And for example, if we look at the official repository for Ubuntu, we can see that there is a nice short description telling us that this is a Debian-based Linux operating system distribution. Then scrolling down, we can find different versions of the image software, few number of collections like 18.04, or a name like Bionic. And these different tags are very helpful when you want to use a version of the software with various setups, so that your code can take advantage of any feature that has been released in the product before, but perhaps may not be available at the moment or supported any longer. Now, whether or not your feature is supported in the latest version, does it affect your code, because you can pull the image of a version that supported your feature set in the past? So, after we've explored this image over here, we've covered a quick introduction into Docker images. I hope you all guys are now clear with it. Now in this session, we are going to explore the Docker image with a little more depth. So without any further ado, let's get start the session. So first up, let's bring back our definition of the Docker image. Docker images are read-only templates, with instructions for creating a Docker container. This offer gives image instructions. Docker will run the image, and then create the relevant container, with any specified dependencies and libraries within the image. Yet this begs the question, where are those instructions defined, and how do we define them to add our own instructions? So the instructions for these images, that create container images, are outlined within a special kind of file, called the Dockerfile. The Dockerfile is a text document that contains various commands that you would use within Docker on the command line to build a container image. For example, it includes commands to specify the base image that you want to base your container off of. Now in the command line, in order to do that, use a command like a docker create, which allows you to use an image and create a container based off of Ubuntu, for example. Now in a Docker file, in order to specify the base image, you would use the firm keyword to achieve the same effect of creating an Ubuntu or Ubuntu container. Notice that keywords in the Dockerfile are pretty distinguishable, because of their all uppercase, scream case syntax. Another example is the command argument, that you would supply as the last option, to create on the command line. In order to give containers a default command like bash for Ubuntu. Now in a Dockerfile, you use the cmd keyword. Dockerfiles have pretty of additional commands, like copy all uppercase, or run all uppercase, to start running a command within the container, and to copy files into a container. So these Dockerfiles are the backbone behind the imaging system of Docker, and therefore they're the secret source of Docker containers. And since containers are the main dish of the Docker entry, this makes Dockerfiles the key ingredient. All the published images on Docker Hub will have a relevant Dockerfile, which defines how that container image was created. So let's look at Docker Hub, and check out some examples of the Dockerfiles hosted there. So if you go to hub.docker.com/explorer, we're gonna see the official repositories for images that Docker Hub officially supports. So back on the list of images, let's choose one to dive more deeply into. Now let's look at this, Nginx Ubuntu, which is a very popular web server that definitely has a lot of support from the Docker community, as well as a high usage rate. So we're going to click on one of these image tags. How about Alpine over here, says we click on this. It will link us to a file on github.com, which is a Docker file. And as you'll see, there is a lot of information, which tells us how the image was created. So we see, we have that from command, and that run command, and well as some various other commands which we'll look at in a moment, and this is a particularly long example. There again, is the copy command, and the cmd command, typical of Dockerfiles to have. So great, as you can see there seems to be a lot to do with setting up the container, with software installations here as well. And now we've discovered the relevant setup to build for this official Nginx image. So the fact that all of these images link to a tag over here, with a Dockerfile, means that we have now a lot of examples to work with, to learn from, and to find best practices for. And overall, it'll just give you more insight into the number of extra dependencies and libraries a particular image needs in order to build. Alright, now that we've explored Dockerfiles more deeply, I hope you all guys are now clear with it. Now in this video, we will see some importance of the Docker container. And then we will compare Docker containers and virtual machines. So without any further ado, let's get started with the session. We have a pretty good handle of what a container is, but we still have a couple of important questions to answer to begin. Well, why are containers useful, and why do they really matter? Containers are great because of their portability. Specifically with Docker, Docker ensures that the same container can run the same way regardless of the operating system environment it's running on. Means, whether you're on Mac OS, Windows, Linux machine, or on a cloud platform, Docker will ensure that your container runs identically, getting the right libraries for your application in the container, no matter where it goes. The only requirement is that the machine has Docker installed. Again, any machine with Docker installed can take your container and run it. Therefore, when it comes to running application-specific code on different systems, developers and engineers can worry a lot less about setting up the environment, and focus more on the application-specific code that drives the real unique value for them and for their companies. This also allows teams and organizations to ensure that their engineers have access to the same code, and more importantly, can execute it successfully on their environments. Finally, this containerization also allows ease of creating multiple environments with their own unique purposes. For example, we can use a container for local development, and then another one to set up a continuous integration environment, where we constantly test the code we're preparing in order to detect bugs. Likewise, we could have another environment devoted to continuous deployment, where we can use a container or containers to actually publish our code to the public, and even tear down or scale up our applications according to new demands as they come in, by scaling down and tearing down how many containers we're using. Docker containers are also very lightweight, which negates one of the biggest downsides of using virtual machines. So you may have also heard of virtual machines, which are another solution to having complete isolated environments in operating systems to run application code or a particular piece of software. Virtual machines are abstractions of an entire computer operating system within a host machine. They virtualize everything, from the entire file system for a kernel, for managing users, and more. However, let's say we want to run an image of software that takes 2 gigabytes. The virtual machine then needs to allocate 2 whole gigabytes of disk space to run that image. If you want to run 5 virtual machines, running that 2 gigabyte image, well, that's 5 images now, 2 gigabytes each, bobbing up our required usage to 10 gigabytes of disk space. Now, let's run the same scenario with Docker. With Docker's containers, you can take advantage of that space, for the 2 gigabytes of usage for that first container, but then share a lot of those resources with any container in the future. The file system between each container is shared, and common files are reduced and don't have to be re-downloaded. So because of that sharing, that 2 gigabytes is efficiently used, and you could theoretically start hundreds of thousands of containers without overloading your host machine space. Having a number of environments on this scale would be too much to handle in the approach of virtual machines, which again need that for 2 gigabytes of space per VM. So both solutions are relevant today, depending on the isolation unit. Perhaps you don't want the files, or even the library files to be shared in any capacity, in which case the VM, or the full virtual machine would be the better option. However, if you need a lot of environments with isolated processes and a solution that is very lightweight, then Docker containers present the better option. Okay, we now have a grasp of Docker containers, as well as the engine. We also got a taste of how these can help development teams and organizations. I hope you all guys are clear with this topic. In this session we are going to create a simple Node.js Hello World Docker container from scratch. So without any further ado, let's get started with the session. So here, as you can see, I am on my desktop directory. Here first, I am going to create a Docker directory. And in this Docker directory, I am going to create another directory called example node. Now, let's open this directory in our code editor. So it is going to start the Visual Studio Code editor. So here first I am going to create a simple Node.js Dockerfile. So let's create a file, Dockerfile, with no extension. Now here first I say, from node 14. It means, which image we want to start from. This will be our base image. In this case it will take the official Node.js image, based on Applin Linux, using node 14. Now let's set our working directory. Which means all our commands will be run in this folder, until we change it again. That's a folder we know already exists in the node image. Now let's copy. And we copy the package.json, packagelock.json using the star means wildcard, and then app.js files that are present in the current folder, into the working directory. Then I am going to say, run npm install, to install the package listed in the package.json file. Then let's expose port 3000 to the outside. A container is 100% isolated from the network unless you expose one of its ports using the expose command. Then we run command node and then app.js to start the app. Note that if we use single quotes instead of double quote in CMD line, then it will result in an error, so use double quote. Now I am going to create another file called app.js, where we will create a simple Node.js app. So here, first of all, I am going to create a variable called express, which is the result of requiring a module or helper library in a node called express. And then, we're going to make an app variable that sets the result of calling this express function that we just created by requiring the express module, which will have 2 more constant variables. Now we're going to use an app function to make a get endpoint. And then this has 2 parameters. The first one is a string, which divides where we want to expose the endpoint. So how about the root of the project? And then we have a callback function, which is going to be in the arrow function format of JavaScript. So that's an opening pair of parentheses, and then an equal sign, greater than sign, which is an arrow function. Then within the parentheses, we can have two parameters, rec and res, which stand for request and response. And then our response, we can send back a string that says, hello world. And with that, we're almost ready. Now we just have to make the server live. So we're going to say, listen, on our port 3000. And finally, it'll be nice to give a message to our user. So let's say, server ready. Super simple, right? But now we have one dependency. We need to add it to the package.json file. So let's open our terminal. And here run the command, npm init -y. Now run npm install express. So as you can see, server ready. Now let's stop the process, and let's create a Docker image from this. So here, I'm going to build a Docker image from this Docker file. So docker, build, and I will give a tag example node, and then a dot. So it will take a while to download the node image, and run the npm install. Then you will get a successful message. Now it's important to note that after you first download a base image like the node one we use here, that will be cached locally, so you don't need to download it again and the image building process will be much faster. So now we can run a container from the image. So I am going to say, docker run, -d, -p, 3000, :3000. Now let's assign a name, node app, example node. Okay, done. So here, you can see, in our Docker desktop, the image is running. And here, let's click on, open in browser button, to open the app running on port 3000. So we have successfully created a simple Node.js container. I hope, you all guys are now clear with it. Now in this session, we will build a PHP image. So without any further ado, let's start the session. Now note that, this lesson is optional, some new concepts will appear, but the function of this lesson will be to show off how Docker can create diverse kinds of images across multiple languages and platforms. I think by having a diversity of examples, we're best equipped to figure out how to create our own custom containers, when it comes to a new language or framework we haven't used before. Alright, let's begin creating this new Docker image. So here, I am on my Docker directory. Now I am going to create a PHP directory, and navigate into it. So mkdir, PHP. Then cd, PHP to change into that directory. Now let's open it up in our code editor. So it is going to open a VS Code editor. Now here I am going to create two files. First one is the Docker file. And for the PHP container, we'll create this index.php file, which will be a server-side generated HTML file with script. So the Docker file will take care of creating the Docker image. But let's start by making the server-side HTML with the PHP with PHP, by having a pair of HTML tags first. Now between these tags, here we can create a PHP tag. So first have a pair of tags. And here both sides we need question marks. And here we say PHP. And in here we write PHP code. So here if we want to generate a string we can use echo. And here let's say hello world, from a PHP container. Here we can write any content, but this is just a nice quick message. So we now have PHP file, with an inner PHP script. Now with the Docker file, let's construct our image. Here on top of the file, we will specify that, we are basing our image of PHP. So I am going to use, from PHP, and here no need to specify a tag since we will use latest by default. Then we will copy our local file, index file, to the container directory, and this will make an index.php automatically. And next, let's specify the default command for this image, that will run once any container based off of its start. We will use the exact format of the cmd keyword, and we will say PHP and -s as our argument. So PHP contain a built-in web server with limited features for app development. It's perfect for our case and we can use it with dashes to serve up the first file that it finds. So then as the final argument for this, we are gonna want to tell it where to host the server. So how about, 0.0.0.0, which is the default route to open connections to the container's ports where its servers are accepting connections. And then with the column we can specify the actual port, which is 3000. So we now have enough to build the image. However, before we move on, let's add a line above our default CMD. The marks that we deliberately are exposing port 3000 within this container. So here, let's say expose 3000. This line now is more informational than functional. It doesn't actually publish the container port to the Docker host machine. Rather it's there so that future developers on the project can know to expose port 3000 when running the container. So now let's build and run the container. So let's open up a new terminal. Now here, let's say docker build from this local path with the dot, then -t, and here I am going to use my username and /php. And we are going to build image. It has to pull up from Docker Hub since we haven't used it yet. But pretty soon it will copy over the index file and then we'll be able to see our running container once we run it from this completed and built image. And there it is. So now we can run this container. Let's call PHP. So use docker run --php. And now we publish a port. Let's say 3000 and 3000. And this is something we know to do again from that expose line. And now we can use our locale built image with username /php. And as we do so, our new container seems to be running. So let's go ahead and visit a new window in our browser. So here we gonna go to localhost, and then 3000, which is our published host port. And here you can see we get hello world from PHP container. So now we have a running container, giving us information from the container. I hope you all guys understand the concept. PHP image. So guys, that's it for now. In this session again we will build one more custom Docker image. We will build a Python Flask image. So without any further ado, let's start the session. So this time, we will create a Python web server image. Now as you can see, I am on my Docker directory. And here, I am going to create a new directory, called Flask. And let's navigate into it. So this one is going to be a Flask Python image, that is a web server. Now let's go ahead and open this up in our code editor. So it is going to open Visual Studio Code Editor. Now here, the Flask image project will need 3 files. An app.py file, which will be the base Python script for the application. Next it will have requirement.txt file, which outline what library dependencies are needed for the Python application. And then most importantly we have the Dockerfile, to instruct how to build the Docker image. So let's make those files. app.py, then requirements.txt, and then finally the Dockerfile. Now let's begin creating this image with the app.py file. We'll quick set up a Flask application to server a message at the root/endpoint. To begin we import the Flask module from the Flask library location. So from Flask, here note that this is lowercase. Then we are going to import Flask module, which is now uppercase. And then we import markup safe, so from jinja2.utils, and then import markup safe. Then we create an app variable, so app, and since app.py is the main file, the scope, in other words this name over here, will be set to the value of main a string, and that name is also __name__. Now this a Python convention, so as long as you have this line, this should set up the app for the Docker container, which is the crucial part. Now we can use this app to set up a root. In Flask to set up a root we use the root function with a special decorator on the app variable. We'll say app.root, it's gonna happen on our /endpoint marked by string over here. Then we provide a method, so let's call this method response, so we'll say def, response, then colon, and then as a result, let's return a string, that says, hello world, and in this time we'll say from S3 Flask container. Let's make sure that we're going to run the application from this app.py file in Flask. It's conventional to check that our scope is main. So if the main variable is truly __, main __, then with a colon after this if statement, we need app.run function, and then we specify with a keyword argument, that our host is the default host of 0.0.0.0 to accept all connections, and then a port is 80. Alright, now we have this app.py file completed. Now we need to complete our requirements.txt file, since a container won't be able to provide the Flask module automatically without properly installing it. So head to requirements.txt, and then we'll specify Flask as a dependency, and then give it a version of 0.12. And then we need 2 more to install. Jinja 2. And its version is going to 3.0.1. And the third one is its dangerous, version as 2.0.1, and a new line at the end of the file. So now we have enough in terms of our Python and Flask files in order to build this Docker image. Now let's go to our Docker file. So first here, let's say from, and let's say use Python version 3. Then let's set a working directory for a container. This working directory is helpful, since any following command like copy and command will now run in the context of this location. Then here we are going to copy the requirements.txt file to the home location, or rather the location set by the working directory. And then let's use the run command to install all the requirements. So let's run pip install -r for open a requirement.txt, and then requirement.txt, so this will install all the requirements that we have specified. And then we copy over all of the code files, so copy, and then 2 dots. Then we are going to expose port 80. And then finally we have default command cmd, then we are going to run Python on app.py. So now we have our Docker file complete, and we can create our Docker image using this. So let's open our terminal. Now let's build this Flask image. So we are going to run docker build a dot. Then we will have our familiar naming convention with username, and then the project name which is Flask. So it will pulls from the Docker Hub the Python image, to take a moment or so to downloading. And soon enough, we have our successfully built image. Now let's clear this. Now I am going to run this container, and create one based off of this image. So docker run, the name is going to be Flask. And then port is going to be 3000. But map it to 80. And then again w3 cloud hub /flask. And as we do so, notice that it says running on the host and the port. So let's go to our browser, and then visit our local host. And as we do so, while we get a message, hello world from S3 Flask container. I hope you all guys are now clear with it. Now in this session, we will explore storage for Docker container, and how we can manage our application data across containers. So without any further ado, let's start the session. Here, the main question we want to answer is, how do we get access to the data from a container that it writes during its lifetime, and then store it somewhere, perhaps on our host machine, so that we can use it for other processes? Now, to achieve storage and manage data, Docker offers 3 solutions, each called a mount. They all relate in that they bring container data to the host machine, however, they have 3 different approaches that can be helpful for various situations. First, we have volume mounts. Volume stored data in a specific directory on the host file system. This directory is managed by Docker. In only Docker container processes can modify this part of the file system. The directory is stored within a special section of the file system devoted to Docker. This is the preferred approach to managing data in a persistent way across multiple container lifecycles with Docker. The data that a container writes during its lifetime stays there, even after the container exits and is removed. Now second, we have bind mounts. Bind mounts are directories that you directly link from the host machine to the Docker container. Therefore, they can exist anywhere on the Docker host's machine file system. Therefore, they can exist anywhere on the host file system. The nice thing about bind mounts is that non-Docker applications and processes can also access and modify that directory, just as well any Docker container can modify the bind-mounted directory. The reason bind mounts are less preferred than volumes is because you're not guaranteed that the data will persist across containers, because of the fact that the data location is stored on the host machine. Luckily, Docker is smart enough to create a bind mounts directory on the host file system if it doesn't exist yet, when you want to create it, but the catch comes with that directory may be moved or deleted during the lifetime of a container or between the creation of multiple containers that depend on the same amount. So bind mounts in a way are less secure than volumes, because they rely and hope for a very particular file system structure of the Docker host. Then finally we have temp-fs mounts, or temporary file system mounts. These mounts don't write to the file system of the host machine. Rather, they write to the memory of the host machine. So this data is never persisted to the disk of the Docker host. Essentially, the temp-fs mount is used during the lifetime of a container to store any data that is not persistent, that could perhaps be secret information. After all, the data will not be saved in the long term on the host machine, nor will it be saved within the container. So it's great for data that is secret, like keys for example, that you want to disappear as quickly as possible. Now here's a diagram that illustrates how each of these storage approaches relate to the host. We have a bind mount, a volume, and a temp-fs mount. The bind mount connects a container to a directory on the file system of the Docker host. Next, we have a volume that connects the container to a directory in the specific area of the host machine. Note that this Docker area is surrounded by a dash box to signal that it's only accessible by the Docker engine and its processes. And finally, we have a temp-fs mount that connects to the container memory, or rather the memory of the host machine, to the container. Now let's go over and review the use cases of each approach to meet the ideas behind each of these solutions a little more substantial. First up, the use case for volumes is when you want to store data across containers on the host system in a persistent way. For example, you may be hosting your containers on an external remote machine in the cloud. The remote machine itself may be running processes that manage and change the file system. However, with volumes, you can store data created across multiple containers running on that host machine in a specific place on the file system. Next, the use case for bind mounts is when you want to edit the directory with non-Docker applications and processes, and you want the container to edit the directory as well. So this may come up if you have a working directory for your project on the host machine, but you also have it set up so that you have configuration files in that directory that you want to go into the container. So for working directories on the host machine, they need to translate to a container. The bind mount is a great solution, especially if you're constantly updating those configuration files. Note that you want your file system to be secure and structured, so that you're guaranteed that nothing will unexpectedly change, or move for a directory that you're depending on within a container. Third and finally, temp-fs mounts are used when you want to work with secret data that should disappear as soon as possible. Alright, the covers of 3 approaches to mounting data to the host machine from a container. I hope now you all guys are clear with it. In this video, we're going to see how we can Dockerize our existing Flask application. So without any further ado, let's get start the session. So as you can see, this is a very simple Flask application. So basically, we've got our normal app.py. Here we're importing the Flask package. Then we're creating an app. And then we're defining a root and view template. And in this case our project directory has templates directory that contains the actual HTML code for our index.html. So guys, this is what the Flask application looks like. And to actually run it, you just hit app.py here. And then here, we are gonna hit run or debug. So now it is running. And now we can confirm that this is working by navigating to the host here, localhost port 5000. And as you can see that everything's working as we expected to. You can see hello world and welcome to the S3 Cloud Hub. So now, I'm going to stop this application. And now what we're going to be doing is, we are going to containerizing this into Docker. Now the very first thing you're going to do is, make sure that you've got a requirements.txt file defined. And in this case, I'm using Flask with version 0.12. And then we're also going to be creating a file called Dockerfile. You need to make sure that you capitalize that D in the Docker file name, because otherwise this won't run correctly. So what's going on here is basically inside of the Docker file, we're telling Docker how to build this particular container or image that you're building And so the first thing we're doing is, we're importing the base image, which is Alpine, and Alpine's really cool, because it's a lightweight Linux distribution. And so to keep your container small and easily transportable between the computers that you're developing on, in this case works pretty well. We're also going to define the present working directory, as well as copying the contents of everything that's right now inside of our IDE into this directory in the image. And then we're going to run pip to actually install all the requirements that we have for our project, which in this case is just Flask. But in your actual project you could have hundreds. And then finally you're defining the command to actually run inside of the Docker container when you're starting it to actually make your Flask turn into a web server. So this is all the code that we're going to have inside of our Docker file. And so the next thing that you're actually going to do here is to create your Flask app. So again, let's open the terminal. And here, we're just going to run the command called docker image, then build-t. And then here, we're going to name this image. So in this case I'm going to call this docker-flask-test. And then here, we need to have space and then period. So once you run this, you'll now see Docker begin to actually grab the other Docker images it needs, and proceed with building your actual image. So we'll let this thing run through. And there we go. So we've got our basic Docker image that's just been built. And so now if we wanted to actually run this image, the first thing we can do is to actually see all the images. So we can run docker image ls. And we can see that we've got that Docker flash test image that we just created. Next, what we're going to be doing is going to docker run. Then we are going to define the port with the -p flag. And here, the first set of characters is defining the port on the host machine that you are going to be allocating to this Docker container. So in this case we're starting the port bindings. 5000 is going to be for this machine that I'm working on. And then the second 5000 is going to be the port on the Docker container itself. So in this case, the Flask application is going to be running on port 5000 of the Docker container. So we're just binding port 5000 on the host to that actual thing on the Docker container. And now, we're also going to do -d to run this in detached mode, so that the terminal is running in a separate window. And then you're going to name the Docker container when it's running. So in this case I'm just going to call it docker-flask-test. Hit run. And you can see how quickly this thing was able to spin up. And so now, if we go and open up our local host, port 5000, we can see that we are now running Flask inside of a Docker container inside of our Windows computer. So that's pretty good. And it makes it a lot easier to ship this container to another computer. So you can develop in a much more easy way. So the other thing we're gonna make note of here is that they basically give you the Docker container id after you've done this. So after you're done playing around, you can copy that. And now what we're gonna do is actually stop this Docker container. So you just run the command docker stop and paste in that id. And then that should stop it from running. So let's try to see if we can get back to this host or not. So you can see that it's now saying that it can't be reached because we've just stopped our Docker container. And then as best practice when you're using Docker, after you're done doing everything with your containers, it's best to run the command docker system prune to free up all the resources like the volumes and networks. So you just do that. Hit yes on the keyboard. And so basically, we've just reclaimed some space from the container that we weren't really using. So there you go. So that is how we can take a Flask application, Dockerize it, then run it, then stop it, and then prune it afterwards. So with this Docker container, if you have Docker installed on your computer, you can check it and you can run it. So I hope you all guys understood the concept. So guys, that's it for this video. I hope you liked it. I will see you in the next lecture. If you have any question or any doubt, feel free to ask in the comment section below. I will answer you as soon as I can. Thank you for watching. Bye and have a nice day.